To begin with, I have climate change in my title, so I maybe want to start with climate change in general. So the human-induced climate change leads to increased temperatures, especially since the 1980s. We can see that in temperature curves all over the world. And we know exactly that humans are the driving factors of this change. This is quite established. And this global climate change also applies to the mountains. So the IPCC report states further that the climate change impacts have been documented in mountains on all continents. A wide range of human and natural systems have been affected by climate change to date. And mountains are especially affected by climate change, which is shown maybe here. So especially since 1980, we see that both temperature curves increase, but the curves for the Alps actually increases twice as high as the northern hemispheric average. So in the Alps we have an increase in temperature of about 0.3 to 0.5 Kelvin per decade, whereas global we have an increase of 0.2 Kelvin per decade. We can actually see these changes in the Alpine systems or the high mountainous systems quite good if we compare photographs. For example, here we have a view of the Gepardschwerner, which is the second largest glacier in Austria. It is an image that was taken in 1905, and we can compare it with the current image of 2019. Which looks now the landscape looks like this. So if you compare it, we see fundamental changes, especially of course the glacial system, but several changes more. Here's another example: the same glacier, another location. We have a photograph from 1920, and we can overlay it by a current image of 2019, so 100 years later, and again we can see huge differences in the systems. So, for example, of course, what comes to the mind first is the glacier retreat within the last 100 years. We can see that quite clearly here on the example of the Gepardschwerner. We have changes in hydrology. For example, we can see here a glacial water stream coming down here in the historic images, or changes in the hydrology in the foreground as well. We have changes in vegetation. Now there are trees growing on that whaleback, which was covered in by glacier in 1920. We have different slope processes. For example, maybe you can see that this lateral moraine is quite active in modern times. So we have a lot of differences and a lot of things we have to be in mind, and that's why we can see these changes in detail now for the next slides. For example, the melting of the Gepardschwerner. You can see here on the right-hand image the extent of the Gepardschwerner at the end of the little ice age. So at 1850 you see the extents on the map, and actually you now see a little animation of the glacier extents for the following years back until 2006. I think this is when the animation stops, so the glacier is shrinking. Now the glacier would actually be around here somewhere in 2020, 2024. And so we have a lot of glacial retreat. The cumulative change of the Gepardschwerner tongue from 1970 to 2080 was over a kilometer in change. Actually, if we consider the extent at 1850, we see that the Gepardschwerner lost over 3 kilometers of its length. We can see changes in the vegetation system, as I said. So the vegetation will continue to migrate upwards. Habitats will disappear, and new habitats will emerge. For example, in proglacial areas. here on this images, you can see a comparison between some 20 years within the Horlachtal catchment of the trees growing up the mountains. Another example here, a comparison of 120 watt years. Again, in the background you can see the emerging trees migrating up the slopes. Then I mentioned the slopes, so they are quite unstable in the current era. So we have again an example from the Horlachtal. Due to glacial depotrescing and the warming of the permafrost, we have instability in the slope. So here you can see an hillshade of a digital elevation model from 2006, and when we compare it to the image of 2012, you can see a large rockfall, for example, and actually you can see more or less the whole slope is moving, so the slope is quite unstable here in this specific location. So we can see a lot of changes here as well. So because we see all these changes in the high mountain areas, there is a lot of going on right now. We decided to establish a research group, which is called SEHAG. SEHAG is short for Sensitivity of High Alpine Geosystems to Climate Change since 1850, so since the end of the Little Ice Age. It's an interdisciplinary and international research group. And we mainly focus, of course, on the high alpine systems, and our main research questions. You can see them here. So first of all, we want to identify significant changes of single processes in these systems, and want to link them to climate change since the Little Ice Age. We want to see how these single processes interact between each other, and maybe there's an enhance or reduce of the impact of climate change within this interaction. Then, last but not least, we want to see how these changes we come across influence the whole reaction of the catchment, so the sediment fluxes, the connectivity, and sediment delivery. This research group, as I said, is quite interdisciplinary, so we have a lot of sub-projects within our group. For example, here we have the sub-project Climate, which is focusing on climate modeling, which is done by the University of Bremen in Germany. Then we have the sub-project Hydro with the Technical University of Munich and the University in Bern in Switzerland. We have the sub-project Bio, which covers the vegetation aspect, which is done by the University of Innsbruck in Austria and IHRR Research in Bolzano in Italy. We have the project Photo, which covers the photogrammetric aspects, which is done by the Technical University of Vienna. And then we have two sub-projects at my institution, so the University of Eichstätt-Ingolstadt. One of them is the Connect, which is covering the connectivity of all the subsystems. And then we have the sub-project Morpho, which covers the morphodynamics, and this is the sub-project I'm working with in my institution. So where do we do our research? We have three specific study areas. You can see that they are more or less north-south oriented through the Central Alps. So the northernmost of these study areas is the Horlachtal catchment. It only has quite small glaciers especially if we compare it to the other catchments. The next one is the Horlachtal catchment, which is just north of the Alpine main divide, which has which is covered by glacier to quite an extent. So 30% of the area is covered by glaciers today. And then we have the Martelltal, which is located in South Tyrol in Italy, so south of the main Alpine divide. And yes, it's glaciated to an extent of 16% of its area. Today, we want to focus on a northern catchment of these three. So the Horlachtal, we can zoom in a little bit and have quite detailed look at this catchment. The Horlachtal is part of the Stubai Alps, and it's a side valley of the famous Ötztal in Tyrol in Austria. Geologically, it consists mainly of gneisses and mica schists. It ranges from about 1,500 meters in the village of Niedertal, which is located here, up to 3,300 meters of the highest peaks. Today there are only small glaciers, so it's glaciated of 1.5%. Today you can see the glacier as they are today marked by these gray areas here. The blue areas here, these are the extents at the end of the Little Ice Age at 1850. There are 3 meteorological stations which are distributed throughout the study area, and we can further divide this catchment into several sub-catchments. For example, first of all, we have the 3 north-south oriented parallel subcatchments, Grastal, GT, this one here. Then we have the Lastigtal, LT here. Then we have the Zwieselbachtal, ZT over here. And then we have even more subcatchments, the main valley, HT here, the Finstertal, FT up here in north, and the Weiteskar, the WK catchment here. And why I choose this study area for the presentation today is because it has a quite high morphodynamic activity, especially on the slopes, and most of this morphodynamic originates from debris flows. And these debris flows in the Horlachtal, they are slope-type debris flows, so they're coming down from the slopes, and most of them have a specific setting. So on top of this, so the first part of this debris flow system is the hydrological catchment in the bedrock section on top of the slopes. So in case of an rainfall event, the water is collected within the ridges of this bedrock section, and then flows downwards to the starting zone where the bedrock meets the talus slope and where a lot of loose material is located. And if a certain discharge threshold is exceeded, then a debris flow might be initiated here. We have the transit zone with the formation of typical debris flow landforms like levees. You can see levees here in this picture. So these little kind of walls left and right of the debris flow channel. And then if the slope decreases, we have the accumulation or deposition zone at the bottom of this debris flow system, where the accumulated material comes to a halt. Here you can see, for example, 2 of these depositions in the Horlachtal. In this video, I hope this hopefully it works. I don't know. No, does not seem like that, but I think that's
To go off the laser pointer.
Off the laser pointer. Yeah, sure. Yeah, thank you. So this is not in the Horlachtal, but in a valley nearby. We can see that we are in a quite heavy rainfall event, and we can see the debris flow on the slope of here coming down. It has a velocity of about 7 to 10 meters per second, and once it reaches the lower part of the slopes, the slope angle is lower, and it comes and the material is depositing here. So we have this debris flow accumulation at the bottom of this slope. So a quite important question, generally speaking, is if frequencies and or magnitudes of debris flows are changing, especially if we think about climate change. And there are some authors that say yeah, for sure there's an increase in debris flow activity, especially since 1980. Then there are others that let's say maybe there's a future decrease in debris flow activity, mainly because we are lacking this loose sediment on top of these slopes. Others say there is no significant trend in this debris flow activity, and then there are opinions that there are major regional differences in between this debris flow activity and the changes within debris flow activity. So in general, we can state that for precipitation-dependent systems like debris flows, the effect of climate change are often not as evident as for temperature-dependent systems like, for example, glacier systems, rock glacier systems, maybe vegetation as well. So it's not that easy. And another problem in terms of debris flow is that debris flows are a quite comparatively low frequency process. So there are not that many. So if you want to investigate changes within debris flow frequencies, we have to look at a quite large time span. So we want to make sure that we have long and complete debris flow records. And that's not easy because high quality data is, especially for the Alps, mainly available since the mid of the 20th century when aerial imagery is available. So that's the reason why many studies start around that point in time, so 1950 around. However, I wanted to increase the time span and go a little bit more into the past. So the questions I want to cover today are, on one side, what temporal changes in debris flow activity in the Horlachtal can be identified since 1850, then what spatial differences there might be, and how can these changes be explained by climatic parameters and maybe can be related to climate change. So at first, I want to have a look at the data that is available for my studies. And as I said just a moment ago, there are orthophotos, so aerial images covering the whole study area, available since about 1950. In the case of Horlachtal, it's 1947. So we have a lot of aerial imagery. We can use structure from motion techniques to calculate orthoimagery with these aerial images that were taken, for example, here by such a camera, which is here on the slide. You can see a Wild RC5 camera. And we can process them into area-wide orthoimageries, like these ones on the left side from 1954 and on the right side from 1973. And what I'm doing now is I compare these ortho images. So for example, on the right side, you can see a small extract of the 1954 ortho image. And especially in the highlighted area, you can see not yet anything. So there's no debris flow related landform. But if we switch to the 1973 ortho image, you can see that there must have been a debris flow in between the data acquisitions. So somewhere in between 1954 and 1973, there was a debris flow event exactly at this location. I can further densify my available remote sensing data by LiDAR data. So there are two data sets, 2006 and 2017, available from the state. So the state of Tyrol processed this data, and then we did our own data acquisitions on 3 different years, 2019, 21, and 22. Actually, we did another data acquisition last year. The 2023 LiDAR data is in post-processing right now. How do we do that? We have a LiDAR scanner. This one here, this is a Riegel Wux 1LR, and we can put it on a helicopter. Then we fly over our study area to create these high-resolution topographical information, 3D point clouds, like you can see here, for example, which enables us to create not only classified point clouds, but also quite detailed digital elevation models. And then we can subtract two different elevation models and create a digital elevation model of difference, a DOD, that shows the topographic changes between the two data acquisitions. So for example, here you can see a talus cone in the DM of 2021. This is the bedrock section, so this upslope, and here is the bottom of the slope, so valley bottom here. We can see some old debris flow landforms on this slope here, and if we compare it to 2022, switch back and forth, and you can see that there must have been a debris flow in between these data acquisitions, right? So the channel is incised even more, and we have a new debris flow accumulation in 2022. Yeah, like I said, we can calculate a DOD, and then we do not only see the difference, so we do not only detect the debris flow, but we can also quantify the transported volumes. So for example, we can delineate this debris flow accumulation zone, and then we can state, okay, these are about 7,800 cubic meters of material, which was deposited in this case here. And this is of course quite nice for us, because here we have not only the accumulation area, which we can map, but we have also the accumulation volume, which we can calculate. And we can then establish a deposition volume area relationship. This looks maybe something like that. So we have these DODs, and then we can plot a deposition volume and deposition area. We get this area volume relationship, and then we can calculate debris flow volumes even for those debris flows where we can only map the deposition area. So even for old debris flows, we can somehow estimate the debris flow volume to a certain point, of course. So that's for the first half of my time span, but there's still a large portion missing, right? So there are no area-wide remote sensing data available for this time, and I was quite a lot thinking about what to do here. I was thinking about historical terrestrial images. However, the Horlachtal was not that strongly visited by tourists in the past, so there are only few of them. Like this nice example from 1905 to 1915. Next, I thought about dendrogeomorphology. Getting information with the help of tree rings. However, most of my study area, or most of the debris flows in my study area, are above the tree line. So might give some useful hints, but I choose to use something else. Another possibility are historical documents, but they mainly focus on large debris flows, which in somehow affected the buildings, villages, and they do not really care about these these debris flows in high areas, in mountainous areas. So there are no really recordings of them. So I ended up using lichenometric dating, or lichenometry, which is a quite useful tool for my task here. So lichenometry dates when a young rock surface was created by measuring the sizes of lichens whose growth rate is known. That means that we can determine the age of the rock surfaces by measuring the lichen diameters of, for example, here, this species Rhizocarpon geographicum. And this method is used since 1950. The first one was special to do that in such environments. It's quite simple and cheap, especially if you compare it to other dating methods. It's a nice tool. However, we have to take some assumptions into account. It's not straightforward. So we have to assume that lichens quickly colonize new surfaces. For example, in my case, if there's a debris flow, lichens are one of the first species to colonize the new surfaces. Then we have to assume that lichens grow slowly, radial, and with a predictable rate, and the lichen growth rates within the specific area are somewhat comparable to some extent. However, they are not comparable if we compare them over a large distance. So for each study area, we have to create our own own lichenometric reference curve, which might look something like that. So we need locations where we know the surface age, and we can measure the lichen diameters. That's a quite challenging topic, because there are not many things, not many surfaces we know the age of in the Horlachtal catchment. One of the main things are the debris flow depositions I talked about right before, which I can map on the ortho photos. So, for example, here you see a debris cone. This is the result of my multi-temporal mapping on ortho images, and you can see that there are some spots where I could possibly go and measure the lichens on, and then I got an idea of the lichen growth rates maybe. However, I don't know the exact age of this. For example, this one of this debris flow accumulation. I only know a time span. So this was the difference between an ortho image 1997 and 2003. So I only know a time span, which is quite a challenging topic. So for most of my reference sites, the ages are interval sensors, so I only know an interval of time. Not for everyone. There are sites I know the date quite precisely. For example, if I found the foundation of an Alpine hut, for example, or quite known glacier extents are useful as well. But as I said, most of the sites, reference sites, are interval censored. This is indicated by this dashed line here. So the true age of my lichen lies somewhere in between this interval. This is a schematic representation, so it's not the real data. It's just so I can show what I did in order to create this reference curve. So the first step is to randomly distribute all the lichen diameter, the ages of my lichens alongside these intervals, and calculate a reference curve. And then I repeat the process for the second time. Again, I randomly distributed the ages, calculated the reference line, and I did that for 10 times, now for 100 times. And somewhen I create kind of a belt of possible reference curves with this method. When I now switch to my actual data, you see that this belt of my actual data is quite narrow, so it's quite nice for me, So this was calculated not only by 100 repetitions, but I used 1,000 of bootstrapping loops. I actually can actually validate my reference line, for example, by using lichenometric dates from other researchers in the neighboring valleys. I can see, okay, they match quite good to my reference curve if I add those data to my plot. So now I established a lichenometric reference curve, and I can date old debris flows. For example, this one. This is an extract of the ortho image of 1947, so the oldest ortho image available, and I can see a debris flow accumulation down here. And of course, most of this debris flow accumulation is now covered by other stuff, for example, new debris flows that covered the old depositions. So I really have to be careful and go to these specific locations where I know they are not overprinted. I can go there, measure the sizes of the lichens, and then I can date these old debris flow deposits. Okay, so now we know the methods are used for creating a debris flow record, and this is what a combined result looks like. So we have a map of the Horlachtal. We see the map debris flows based on the remote sensing data. We see the lichenometric dates marked with these points as well. And what comes to the mind maybe quite intuitively is that there are quite a lot of debris flows. So in total I have 991 individual flows identified in the study area since 1947, so with the help of the remote sensing methods. And I see that they are not uniformly distributed. So most of them focus on the three north-south orientated subcatchments GT, LT, and ZT. And I even can see this when I plot a timeline underneath the numbers of debris flows for each subcatchment. So, and I want actually to draw your attention to the time span 1990 to 1997, because we see a quite interesting thing. We see that here, for example, especially GT and LT show a lot of debris flows within this time frame, but all the other subcatchments basically more or less nothing. And that's quite interesting. And the question that comes to my mind is what causes these small scale differences. So actually, as I can see, there are huge differences on the spatial scale, but what causes this? And to answer this, I can jump to the July of 2022. I have a hunting camera installed in my study area, which sends one image of one of the debris cones each day to my mail server. So I can have a look, for example, here, 20th July of 2022, and then I got the next picture of the following day, and you see, especially in the lower right corner of the image, that there was a large debris flow event. In between those two images, you can see another debris flow accumulation hidden behind the tree as well. So there were some debris flows. I then can look at the precipitation data of that specific day. So these are radar precipitation data from the 20th of July, and you can see we are now at 2 p.m. and we can see basically nothing. So there's no precipitation around here. We skip 1 hour, now it's 3 p.m. and still not really precipitation, maybe some clouds in the southwestern corner. But now we skip to 4 p.m. and we have this quite local, large, quite local but heavy intensities in some parts of our catchment. So the precipitation intensities of up to 50 millimeters per hour right now. An hour later or 2 hours later, everything's gone up again. So it was quite a local, high intensity, short duration rainfall event that caused these debris flows. And we can even see this local character of this cell, of this thunderstorm, when we have a look at the discharge data of the study area. So here you can see this peak in discharge quite well. Another station shows the same peak at the same time. We have another station that even crashed because of the heavy bed load during the event. But then we have a discharge gauge which basically shows, more or less nothing. So it's quite, this is why we have such a high variability on the spatial scale when we saw based on the debris flow mapping. So these local high precipitation, high intensity precipitation events, they cause this spatial changes or spatial differences on a quite local scale. In total, this event of July 2022 triggered 156 debris flows in the catchment area. We know that because we have quite good and detailed data. So we have a area-wide pre- and post-event LiDAR data set, which is quite nice for us. We have precipitation data, we have discharge data of the event. And so we can create something like this, for example. You can see the accumulation volume of each of the 156 debris flows based on the DOD created from the LiDAR models. And we can see that there's a relationship between the debris flow volume and the amount of rainfall per debris flow catchment. So there's a relationship. It's not that it's a quite good relationship because they vary within 2 orders of magnitude. The scales are logarithmic. But at least we see a relationship, and this is quite nice to see, especially when it comes to debris flow modeling or stuff like that. So, in general, when we want to characterize the spatial features of the debris flows in the Horlachtal, we can say that they mainly focus on some specific subcatchments. These differences are caused by very local, heavy rainfall events, and the occurrence and magnitude of debris flows depend on the rainfall intensities and the morphometric properties of the hydrological catchments of the debris flows. We can have a look again at this figure right here, because we cannot only analyze the spatial differences, but we can have it on the temporal scale as well. So here you can see the numbers of debris flows per year for the remote sensing time frame, so since 1947. As you can see, you might think, or you can guess that debris flow activity is increasing since 1950 about. So that's what I thought when I looked first at this graph and say, okay, debris flow activity is increasing. Or is it? So we can have a a more detailed look at this thesis. So we can not only have a look at the numbers of debris flows per year, but also at the deposit volume per debris flows, deposit volume per year, and we can see right away that this high peak between 2010 and 2015 disappears to some extent. So it shrinks quite largely when it comes to debris flow volumes. We can even calculate the mean accumulation volume per debris flow for each time frame, and then it's not that clear anymore. It's more like there are some active periods. So for example, this might be an active period. Here we have another one, and maybe we are starting another one right now. So it's not that clear anymore. And there are other problems as well. For example, the quality of the remote sensing data is increasing within my time frame. So I compare an aerial image of 1947 with a modern high precision LiDAR scans. This means that I might miss small magnitude events, especially in the earlier data sets. Then another point is that the time interval between the two data sets increases. So we have a quite large time span here. And that means that we have a huge problem of overprinting of debris flows in old intervals, for example, by new debris flows or by vegetation cover or something like that. So It's not that straightforward to say debris flow activity is increasing in my study area. To maybe get a better overview of this temporal trend, I can add my lacinometric data, I won't go into detail right now to especially for the dates here. I just wanted to say that I dated 47 different debris flow depositions and can even detect debris flow active period at 1850, so at the end of the Little Ice Age. When I analyze all the lacinometric data together with the remote sensing data, I got something like this. So I got periods with high magnitude debris flow events. One period I can definitely say is around 1850. Another one is around 1900. Another one is between 1930 and 1942. And then there are the remote sensing based periods between in the 50s and 60s, in the 90s and early 2000s, and maybe from 2022 onwards. So it's not that obvious anymore that we have an increasing trend in such debris flow activity in the Horlachtal. Not really in the frequency, but we can, but on the magnitudes as well. So there's no fundamental change in a debris flow system that I can state with, for sure. But if I want to say, okay, if I want to relate my findings, I can maybe use the triggering events, so the high intensity, short duration rainfall events that triggers the debris flows, because I know that these events trigger the slope type debris flows in Horlachtal, and if these triggering events change, the debris flow dynamic has to change as well. So I wanted to analyze precipitation data. However, one main point I came across is that daily rainfall sums are not very meaningful for this analysis I wanted to do, and I want to show you this here in this slide. So this is a table which analyzes precipitation measurements from a specific data set. It's a meteorological station in the Alps somewhere, and it measures or it analyzes the precipitation data in two different ways. So the upper half analyzes it based on 15 minutes intervals, and then the lower half based on daily data. So they aggregate the data to daily sums. We have two different periods. So we have, does not matter the exact numbers, that do not really matter. We have two periods, an older one and a newer one. And in the 15 minutes data, so these which represent these high intensity events, we see that the classes with the high numbers, so high numbers of precipitation, they show a negative change, so actually decrease in such event. And at the same time, the same data show an increase in the high classes for daily data. So there's this does not go together well. So we have an increase in daily sums, but at the same time a decrease in these 15 minutes data sets. So this is why I wanted to make sure not to use daily rainfall sums, because there might be problems with this. However, most of the papers use, of course, daily sums, because such sub-daily data is very hard to get. So, for example, the largest sub-daily data set in my study area is writing since 1989. And this time span is just too short to make a good statement about the frequency of high-intensity events. So the precipitation data from meteorological stations have some some problems for my topic. So the spatial resolution is too low because I'm focusing on quite local, high intensity events. The time series are not long enough, and the transferability between larger distances are not given. So there's a kind of a problem here. So I wanted to switch the method, and this is where my project partners from the University of Bremen comes into play. They are climate modelers, and they used a dynamical downscaling to create a kind of local climate model, especially for the Central Alps with a spatial resolution of 2 × 2 kilometers tiles and a temporal rainfall resolution data set of 15 minutes, which is quite nice for my purposes, and a final time frame from 1850 to 2015. With this large and huge data set, I can produce several outputs, like, for example, here some fancy figures showing the mean temperature between 1850 and 2015, which is quite nice. But on the other hand, I can see that we have a quite nice precipitation data set as well. For example, here you can see the precipitation on late summer of 1882. My study area is the northern one here. So quite fascinating data set here. And I can analyze the tiles which are over my study area, so over the Horlachtal, which are 30 tiles in total. And for each tile, I can analyze the heavy rainfall events. So, for example, it may look like this then. So, for example, this is tile number 69, and I can see plot the number of heavy rainfall events per decade for this tile and see a slight decrease in these events. However, the p-value states that it's not really significant. So more or less no change in these events for this tile. I can do this for all of the tiles, and then I can see quite nice results. For example, I can see major spatial differences. There are tiles with few of these events, and then there are tiles with many of these events, and it seems like they are grouped. For example, these one, and these actually are the lowest ones, my lowest tiles. So this is the main valley, which is coming up here. So the Ötztal, which have these low altitudes, and here I have these few modeled precipitation events as well. Throughout the whole data sets, I see no clear temporal differences. There are some slightly negative trends, but most of them are not significant. So basically, I cannot see any trends in these heavy rainfall events in this modeled data set. So now I can combine my findings of the debris flow mapping and lichenometry survey together with the heavy rainfall events since 1850. And then I can create figures like that. Here you can see again the number of days with such heavy rainfall events per decade. This time it's a summary of all of the 30 single tiles. On the other side, figure number B shows the high peaks of such events. So if there are single events with especially high rainfall intensities, and then the blue background colors indicate my debris flow events that I detected. So they go quite well together. The first period is quite tricky because I dated it with lichenometry. And when I see the precipitation data, I might want to shift it slightly to the right So it matches with this high number of precipitation intensities in the 1860s. The second period is quite nice because there are not many of high precipitation events here, but there is the second largest single event within this period. Period number 3 shows a lot of days with precipitation events. Period number 4 shows kind of medium events, but there are high peaks as well, high single peaks. And period number 5 shows not only very high or many days with high precipitation events, but as well the single, the highest peak of the single events as well. So they go quite well together. To conclude my talk here, I wanted to just state what I've shown during my presentation. So I established a debris flow record since 1850 using remote sensing and lichenometric methods. I created this nice plot which shows no clear indications of increasing or decreasing trends in debris flow activity. I then can state that the frequency and magnitude of such debris flows showed significant spatial differences, and these are caused by the local characters of such triggering rainfall events, which we saw, for example, in 2022, and the number of such events show, at least in the model data, no significant trend since 1850, but a huge spatial variability as well. So to summarize everything, I can say that to date there have been no clear trends, clear effects of climate change on a debris flow system in the Horlachtal specifically, and the heavy rainfall events, neither the heavy rainfall events nor the detected debris flow activity show significantly any temporal changes since 1850. And that's it for my talk. I thank you very much for your attention. I'm here for any questions.